This is homework 2, part A of process dynamics and control. And what we're doing today is we're taking a 100-liter tubular flow reactor, and we're separating it into like 100 perfectly mixed sections, and we're going to simulate back mixing. So we're going to simulate and plot the concentration profile along the tube on a rectangular pulse of a height of 3 moles per liter and a width of 1 minute is superimposed on the nominal 1 mole per liter inlet flow of 100 liters per minute. So I've already gotten started, and I have our script here to access all of the NumPy and SciPy stuff. And I've also already put in our variables and our values that we're going to use. So we have our 100 sections from our tubular flow reactor, our total volume, which we're going to use, which is 100 liters, the equation for the volume per section, which is just the total amount of liters divided by how many sections. Then I have our inlet flow rate, which is 100 liters per minute, our initial concentration, which is 1 mole per liter, and this is an array, just stating that each section is going to have the same initial concentration, and then our duration period, which is 10. So let's get started. We have two things that we need to define. So we're going to start with our function sigmoid, which is x naught, which equals 0, and then our width, which equals 1. And then we're going to return with speed dot special expert. Then our x naught, or x, and then x naught will equal 0, and then our width will equal width. There we go. And then we're going to define our pulse. So I knew I did something a little wrong here. So this is actually supposed to be x minus x naught, and that to be divided by width, and this is just creating random numbers between 0 and 1, basically to be used as like the inlet concentration, and that's going to be used in our pulse. So let's get to the width equals 1, and our pulse is just saying these are our variables that we're going to be using, and we're going to return with our equation, which is C, and then C1 minus C2. It's going to multiply by sigmoid, and then our function, which equals x1, and then width, which equals width, and then we're going to subtract, and we're just going to take this equation essentially, copy and paste, and we're just going to change this to x2. And there we go, everything works. So just to run down, this is basically creating a random number between 0 and 1 to represent our inlet concentration, and this is just going to create that inlet concentration and over time essentially. So this is creating our plot, but we need a way to actually display that data, so we're going to go ahead and display it. Now to plot it, we're just going to go ahead and make our p dot line space. Okay, I'm gonna use, so for the 10 units of time, we're gonna have 1,000 data points. That's what it's saying. And then we're gonna have our fig equals make underscore subplots. Fig dot add underscore subplots. Sorry, not subplots, scatter. And then we have our x, which equals x, and then our y, which equals our pulse function, and our parameters are x, and then we're going to have 1, 2, 1, and 3, and then 0.01. So I think that should be good. Another thing to note, I changed the C1 minus C2 to a C2 minus C1. The plot becomes a little different. It still is different. One sec. Okay, so it did work. I just hadn't pressed run all for this to take place, so we kind of just used the graph before, I guess. But yep, so here's the plot. This is what it should look like. Here's our pulse. And as you can see, it's going from 1 to 3, as we stated in our pulse parameter per se. And there we go. And then we're going to head on to the next part of this. Okay. Now for this next portion, we're going to go ahead and define our right-hand side. And we're going to use t and then vector. And then we're going to define what our inlet concentration is, which is going to be our pulse in terms of time. We're going to have 0, 1, 1, 3, and 0.01. And then we're going to define what our concentrations are, which is our vector. What we got is we're going to define our changing concentration, or DC, which is NP dot zeros in terms of N. Then we'll go ahead and make our, array. C0 is Q times Cn minus CO, and all that divided by volume. And then we're going to have DC starting from our first value over, and Q times we will have C emitting our first value minus our C, which requires all our values, and that will be divided by volume. And then we're just going to go ahead and return our change in concentrations. Should work. Alright, great. And then we'll move on to the next section. This next section we're going to do our solve IVP stuff so that we can get ready to plot this. So we're going to go ahead and start with n times, which is how many times we want to run this. So we're going to pick 10. And then we're going to go ahead and, our t-plot, which we're going to go ahead and do np.line space. We're going to have 0, t-end, and then our n times. Then we're going to go ahead and do our res, which is sp.integrate.solve _IVP, this is where we're going to go ahead and do our Jess, and then we're going to have our 0 to 10, oops, not O, and then our initial concentration, our method, which we're going to use as Riddell, and then our dense output will be true. Then our so our profiles, our concentration profiles will be res dot sol t plot, and this is our like more over the math for making this plot, and then we're going to go ahead and make that plot. We're going to go ahead and start with fig equals make underscore subplots, and then for our t index we're going to go as range n times, and then we're going to do our fig dot add underscore scatter, where our x is equal to np dot arrange in terms of n, and our y is equal to our concentration profiles with terms of t index. I believe that's it. And then we're gonna go ahead and do our figure. I'm just gonna press run all so we can everything. Okay, there we go. And yep, this is our plot. As you can see, at 20, we're going to spike up to around 20, I would say. 324 around is where our spike occurs to 3 for concentration. If we go ahead and add these plots, it seems like our pulse kind of happens at our end of the pipe, where especially with this one right here, which is trace 3 going first, but it seems like at the end of the pipe is when our spike occurs.